Hello everyone, welcome back to MP Coding's Linux device driver development with Raspberry Pi tutorial series. Today, we're starting a new section, Linux device model and Sysfs. If you've been following the series, we've touched on these topics before. But we never really went deep into what's actually happening under the hood, how the kernel manages devices, drivers, and the connections between them. So in this section, we're going to do exactly that. We'll dive deep into the theory behind the Linux device model and Sysfs. And in this video specifically, I'll be covering the Linux device model, what it is, why it exists, and how it works. All right, let's get into it. Before Linux 2.6, every subsystem managed its own devices in its own way. No shared model, no unified power management, no consistent hotplug support. It was basically every subsystem doing its own thing. The Linux device model, or LDM for short, was introduced to fix exactly that. It maintains a single internal data structure that reflects the state of the entire system. What hardware is present, how it's connected, which driver owns it, and how it can be powered down. Now, the kernel uses 5 core entities to model the system. The first one is the device, which represents a physical device attached to a bus. Then we have the driver, the software that can bind to a device and operate it. Next is the bus, the communication channel that connects devices to the processor. After that, we have the class, which groups devices by what they do, not by how they are connected. For example, all disk drives belong to one class, all serial ports belong to another, regardless of what bus they sit on. And finally, the subsystem, which gives a high-level view of the entire system, covering devices, buses, classes, and modules. All of this is exposed to user space through the Sysfs virtual file system, which is mounted at /sys. I'll drop the reference link I used to build my explanation document in the description. It's the official Kernel Labs page, so if you want to go even deeper, definitely check that out. First, let's understand the kernel object, or Kobject, because this is the foundation of everything in the Linux device model. Before buses, devices, or drivers, there is struct Kobject. It's the primitive that every LDM structure is built on. It provides 4 key things. A name, which appears as a directory in Sysfs. A reference counter, called kref. The object is only freed from memory when this counter hits 0, so the kernel always knows whether something is still in use. A parent pointer, which is how the hierarchy tree gets built. Every Kobject knows who its parent is. And the kset, which groups sibling objects that live at the same level in the hierarchy. Now, if you remember from the last video where we created a Kobject, you actually saw this struct in action. And here's an important design decision Linux makes. It uses composition instead of inheritance. If you come from a C++ background, you might expect a universal base class that everything inherits from. Linux doesn't do that. Instead, it embeds struct Kobject inside higher-level objects. This gives every kernel object a common lifetime model, a Sysfs representation, and a place in the hierarchy, while still letting each subsystem add its own data on top. So the key rule to remember is, struct Kobject is almost never used on its own. It's always embedded inside something bigger, like struct device, struct bus_type, or struct cdev. And when we need to get back to that outer struct from a Kobject pointer, we use container_of. Actually, we already did exactly this in the last video. In the dedicated work queue example, we used container_of to walk back from an embedded member to the outer struct. Same concept, same pattern, just applied here at the device model level. Now let's talk about buses. A bus is the communication channel between the processor and I/O devices. In the Linux device model, every device is connected to a bus, even if that bus is a virtual one with no physical hardware behind it. A good example of that is the platform bus, which is what the Raspberry Pi uses for hardwired SoC peripherals like GPIO controllers and UARTs. When a bus is registered with the kernel, it shows up under /sys/bus/directory. Now, the struct bus_type is what describes a bus in the kernel. Here are some of the properties it provides. The two most important callbacks are match and uevent. The match is called whenever a new device or a new driver appears on the bus. It compares the two and returns non-zero if they're compatible. This is the function that decides whether a driver gets bound to a device. The uevent is called just before a Hotplug event is sent to user space. Its job is to inject environment variables into that event, which tools like Udev can then read and act on. If I show you the currently registered buses on the system, inside /sys/bus/, you can see things like SPI, I2C, USB, and many others. We've already worked with I2C and SPI in earlier videos. How the bus works, how a new device node gets added to it, how the driver binds. All of that follows the same model we're describing right now. If I pull up our SPI example, you can actually see this hierarchy in action. Inside the SPI_device struct, there's an embedded struct device. And inside that, you'll find the Kobject and the bus_type structures. That's exactly the composition pattern we talked about with Kobject. It flows all the way down. So, if we want to register the custom bus, here, I have added how we can do that. So what's happening here is pretty straightforward. We define a bus_type struct and give it a name, my bus. Then we wire up our two callbacks. The my_match function does a simple name comparison. If the device name and the driver name match, it returns non-zero and the kernel proceeds with binding. The my_uevent function adds a custom environment variable called dev_name to the Hotplug event. So when user space receives that event, it knows the name of the device involved. Then in module_init, we call bus_register, and our bus appears under /sys/bus/mybus. On exit, we call bus_unregister to clean it up. Now, buses can also expose their own attributes as files under system bus directory. These are just readable and optionally writable files that give you information about the bus from user space. We use bus_attr, bus attribute, to define them. So here, bus attribute defines an attribute called DESCR with read-only permissions 0444. It links to my_show_desker, which simply writes the string LDD tutorial bus into the buffer when that file is read. In module_init, we call bus_create_file to actually create the file at /sys/bus/mybus/desker. And in module_exit, we remove it with bus_move_file. So after loading the module, if you just cat /sys/bus/mybus/desker from the terminal, you'll get that string printed out. Simple, but it's a clean way to expose bus-level information to user space. Next, let's talk about devices. Any physical or virtual device in the system is represented by struct device. And just like we said with Kobject, struct device is almost never used directly. It's always embedded inside a bus-specific structure, and you get back to that outer structure using container_of. All registered devices appear under /sys/devices. So let's look at how we define a bus-specific device type. We create our own my_device struct, and inside it we embed a struct device. We also keep a pointer to the driver and a name. That embedded struct device is what the kernel works with. Our own fields sit around it. Then we define a parent device called my_bus_device. This represents the bus itself as a device in the hierarchy. Think of it as the container that all devices on this bus will sit under. It gets an initial name of mybus0 and a release function, which in this case does nothing, but it has to exist. Then we have my_register_device. This is the function the driver side will call to put a device onto the bus. Inside it, we set the bus, set the parent to our bus device, assign the release function, set the device name, and finally call device_register. We also export this function with export underscore symbol so other modules can use it. And my underscore unregister underscore device does the reverse. It calls device underscore unregister to remove the device from the bus. And it also exported. Now on the driver side, inside my driver.c, using that exported API is straightforward. We declare a my underscore device instance, give it a name, mydev0. Wire up the driver pointer, and then call dev underscore set underscore darv data to store a pointer to our full my underscore device struct inside the embedded struct device. This is important. It's how we get our private data back later when the kernel calls probe or remove and hands us only a struct device pointer. Then we call my underscore register underscore device to put it on the bus. Now, just like buses had attributes, devices can have their own attribute files too, visible under /sys/devices/mybus0/mydev0. The my underscore show underscore type function is the read callback. Notice what happens inside it. This is container underscore of an action. The kernel gives us a generic struct device pointer, and we use container underscore of to walk back to our full my underscore device struct. Then we just write the device name into the buffer. Device underscore attr, device attribute, then wires this up as a read-only attribute called type. After device underscore register, we call device underscore create underscore file to create that file in Sysfs. And before device underscore and register, we call device underscore remove underscore file to remove it. Always in that order. Create after register, remove before unregister. Now let's look at drivers. A driver registers itself with a bus. When a new device appears on that bus, the bus core calls match. If it returns non-zero, meaning the device and driver are compatible, the bus core then calls probe to bind the driver to that device. That's the whole binding flow in one sentence. Driver information is spread across a few places in Sysfs. You'll find the loaded module under these directories. So just like we did with devices, we define a bus-specific driver type by embedding struct device underscore driver inside our own my underscore driver struct. The module pointer is there to track which module owns this driver. Then my underscore register underscore driver sets the bus pointer on the embedded driver and calls driver underscore register. And my underscore unregister underscore driver calls driver underscore unregister to remove it. Both are exported so the driver module can call them. Now on the driver side, in my driver.c, this is where probe and remove actually live. In my underscore probe, the kernel hands us a generic struct device pointer. The first thing we do is use container underscore of to get back to our full my underscore device struct, because that's where our actual hardware data lives. Then we do whatever initialization the hardware needs. Here we're just printing the device name. But in a real driver, this is where you'd map registers, request IRQs, and bring the hardware up. In almost every example we talked about in earlier examples, we implemented a device driver here. In my underscore remove, same idea. We clean up whatever probe set up. Then we define our my underscore driver struct. Notice the driver name is set to mydev0. And this is important because our my underscore match function on the bus does a simple name comparison. So this name has to match the device name exactly for the binding to happen. Finally, in module underscore init, we call my underscore register underscore driver. And in module underscore exit, we call my underscore and register underscore driver. Once the driver is registered, the bus core takes over. It runs match against every known device, and if something fits, probe fires automatically. Now let's talk about classes. A class is a functional grouping of devices, and the key word there is functional. It doesn't matter what bus a device is on or how it's physically connected. What matters is what the device does. A good example of this is storage devices. A USB disk, a SATA disk, and an NVMe disk are all connected through completely different buses. But from a user's perspective, they all do the same thing. They store data. So they can all appear under a similar functional interface. That's exactly what a class represents. All block devices form a class. All serial ports form a class. And you can define your own as well. Classes appear under /sys/class directory. Now, the biggest practical reason to use classes, and this is the one that matters most in day-to-day driver writing, is automatic /dev node creation. When we call device_create, it places a dev attribute file under /sys/class. That file contains the major and minor number of our device. Udev reads that file and automatically calls mknode to create the /dev node for us. No manual mknode call required. This is the bridge between our driver and user space. We discussed this in the character device driver example, how to automate /dev node creation for a character driver. If you don't understand how it works, please go and watch that video. The class API works in 2 steps. Step 1 is registering the class. We do this once at module init. We define a struct class with a name and an owner, then call class_register. After that, our class shows up under /sys/class/myclass. On exit, we call class_unregister to clean it up. There's also a shorthand for this, class_create, which allocates and registers the class in a single call. It's more commonly used in practice because it's cleaner. If it fails, we check the error. On cleanup, we call class_destroy instead of class_unregister. Step 2 is creating a device under that class, and this is typically done inside probe, or right after dev_add, if we are working with a character device. We call device_create, and this one function does 3 things at once. First, it initializes a struct device and links it to your class. Second, it creates a directory under /sys/class/myclass/myclass0/ and puts a dev file inside it. That file contains the major and minor number in major, minor format. And third, it fires a uevent. Udev picks that up, reads the dev file, and creates /dev/myclass0 automatically. On cleanup, the order matters, always reverse. Call device_destroy first, then class_unregister or class_destroy. If we do it the other way around, we will have dangling references and the kernel will not be happy about it. Now let's talk about the real meaning of probe and remove. Most engineers think Linux driver writing is just module_init. Register your driver and you're done. But Linux doesn't work that way. The real lifecycle is controlled by the kernel's binding engine. And understanding this is what separates someone who just writes drivers from someone who actually understands what's happening. To understand this, let's think about how a driver actually gets loaded at boot time. And for this, we need to talk about the device tree. Now, I've touched on the device tree in the I2C and SPI examples earlier in this series, so you've already seen it in action. But we haven't gone deep into device tree overlays yet, and those dedicated device tree videos are coming later in the series. So for now, don't worry about the details. Just think about this one scenario, the SPI driver loading at system boot. When the Raspberry Pi boots up, the kernel reads the device tree blob, the DTB. This is a compiled description of all the hardware on the board. The kernel walks through it, finds all the hardware nodes, and creates platform devices from them. At that point, the SPI driver is waiting. The bus core runs match between the platform devices and the registered drivers, finds a compatible string match, and then, and only then, calls probe. Now the driver is bound. The hardware is ready. And from user space, you can now access the device through /dev/SPI 0.0 or through the Sysfs entries we talked about earlier. That's the moment probe completed successfully, the device is alive. Now the other side of that coin is remove. When the kernel decides to detach the driver from the hardware, whether that's because of RM mod, a device unbind, or system shutdown, remove is called. And your job there is simple, leave cleanly. Stop any DMA transfers, timers, or work queues that are still running. Disable IR queues safely. Unregister your device nodes, and put the hardware into a safe state before you let go of it. Once remove returns, the driver is unbound, the hardware is in a safe state, and all resources are released. The system stays stable, nothing leaking, nothing dangling. And that's the full life cycle. The kernel brings your driver to life through probe, and it takes it down cleanly through remove. You don't control the timing, the kernel does. Your job is just to handle both ends correctly. Here, these are the explanations of above example. So read these also. Now let's understand Hotplug and Uevents. Hotplug is the ability to add or remove a device while the system is running, without rebooting. And a uevent is how the kernel notifies user space when that happens. Now here's the important connection. Uevents are tied directly to Kobjects. Whenever a Kobject is added or removed from the kernel, a uevent is fired. And because every struct device embeds a Kobject, creating or destroying a device automatically triggers a uevent. You don't have to do anything extra. It happens as part of the device model. Let's walk through the flow. It starts when a Kobject is created or destroyed. That triggers a call to Kobject_uevent. With either Kobject add, Kobject remove, or Kobject change depending on what happened. That event is then sent through a netlink socket to user space, where udevd, the Udev daemon, is listening. Once udevd receives the event, it does three things. It applies whatever rules are defined in /etc/udev/rules.d/. It creates or removes the corresponding /dev node. And if needed, it loads the required kernel module automatically using the mod alias variable through modprobe. So the whole chain, from a device appearing in the kernel all the way to a /dev node showing up in user space, happens automatically, driven by this uevent mechanism. We will see all of this working in the example coming up in a moment. And in the next video, we'll go deeper into the Sysfs interface. But before we go to the example, I've put together a full Sysfs map that shows how everything we discussed today, buses, devices, drivers, and classes, all comes together under /sys. Take a look at that. It's a good reference to keep in mind as we move forward. Now let's look at a real example that brings everything we discussed together. I have created a simple but complete implementation of the Linux device model from scratch. We have 3 kernel modules, a shared header file, a make file, and a readme. Let me walk you through each one. The first file is mybus.h. This is the shared header, and this is the contract between all 3 modules. It defines 2 structures, my_device and my_driver. And notice what's inside them. My_device embeds a struct device, and my_driver embeds a struct device_driver. That's the composition pattern we talked about, wrapping the generic kernel objects inside our own structures. The header also declares the bus registration API functions so all 3 modules can see and use them. Now let's look at mybus.c. This is the core of the example. This module does 3 things. It creates the bus, registers a parent device, and exports the registration APIs for devices and drivers. First, the bus itself. We define my_bus_type with a name of mybus and wire up our my_match function. The match function is dead simple. It just compares the device name with the driver name. If they're equal, it returns non-zero, and the kernel proceeds with binding. And we export the my_bus_type. Then we have the parent bus device my_bus_device with an initial name of my_bus0. This is important. Every device in Linux lives in a hierarchy, and this parent device is what sits at the top of ours. When devices register, they'll appear as children under this in Sysfs. Then we have my_register_device. When it called, it sets the bus pointer, sets the parent to our bus device, assigns a release function, sets the device name, and calls device_register. This is what actually puts the device into the kernel's device model, and we export this function, so mydevice.c can call it. Same idea for my_register_driver. It sets the bus pointer and calls driver_register. And this also exported. So, my driver_c can use it. In module_init, we register the bus first, and then register the parent device. So order is matters in here. The bus has to exist before anything can attach to it. And in module_exit, we reverse that, unregister the device first, and then unregister the bus. Next is myDevice.c. This one is straightforward. It creates one my_device instance with the name mydev0. And in module_init, it calls my_register_device. That's it. The device is now on the bus, sitting under my bus0 in Sysfs. On exit, it calls my_unregister_device to remove it cleanly. Now my driver.c. This is where probe and remove live. We define a my_driver struct and set the driver name to mydev0. And this is the critical part. Remember, our my_match function compares device name to driver name. So this name has to match the device name exactly. That's our binding contract in this example. My_probe is called automatically by the kernel when the match succeeds. It receives a generic struct device pointer, and in a real driver, this is where you would use container_of to get back to your full my_device struct and start working with your hardware. Here we're just printing to confirm it was called. My_remove is called when the driver is unbound. Again, in a real driver you would clean up hardware here. For now, we just log that it was called. In module_init, we call my_register_driver, which registers the driver with our bus. And here's the moment it all comes together. The kernel immediately scans all devices on the bus, calls my_match, finds mydev0, then matches it, and calls probe automatically. We do not need to call probe manually. The kernel will do it automatically. Now let's look at how to actually run this. Open the terminal inside the example directory. Now type make and hit enter. Now wait for it to build all the 3 kernel modules. You should see all 3 kernel modules get compiled without any errors. Now, before we start loading modules, let's open 2 more terminals. In the first one, we will watch the kernel log messages live. In the second one, we will monitor Udev events. Run udevadm monitor and leave it running. Keep all 3 terminals visible at the same time, because when we load each module, you'll see things happening across all 3 simultaneously. That's what makes this demo really interesting. Alright, let's load the first module. In the main terminal, type sudo insmod mybus.ko and hit enter. Now look at the kernel log. You can see mybus init printed, followed by mybus registered. That tells us 2 things happened. The bus was registered successfully, and the parent device mybus was registered on top of it. That's the uevent mechanism we talked about. The moment a Kobject is added to the kernel, user space gets notified automatically. Let's verify what got created in Sysfs. Run ls/sys/bus/mybus. And there it is. The mybus directory exists under /sys/bus, with devices and drivers subdirectories already waiting inside it. Now run ls/sys/module/mybus, and this directory was created too. This is where the kernel tracks the loaded module itself. Now let's load the device module. Type sudo insmod mydevice.ko and hit enter. Look at the kernel log. You can see mydevice init printed, followed by mydevice device registered. So the device is now on the bus. But notice something, there's no probe message yet. That's because we haven't loaded the driver module. The device is sitting on the bus, waiting, but there's nothing to bind to it yet. Now look at the Udev monitor. You can see events firing for devices /mybus0/mydev0 and module/mydevices being created. So the moment we registered our device, The kernel fired a uevent and user space was notified immediately. Let's verify in Sysfs. Run ls/sys/devices/mybus0, and there's my dev0 sitting right under its parent my bus0. That's the hierarchy we set up in the code, the parent device on top, and our device as a child underneath it. And run ls/sys/module/mydevice. That directory is there as well, tracking the loaded module. And now the moment everything has been building up to. Let's load the driver module. Type sudo insmod mydriver.ko and hit enter. Look at the kernel log. You can see mydriver init printed. But right after that, without us doing anything else, you can see mydriver probe called from mydev0. That's the kernel's binding engine doing its job. The moment the driver registered with the bus, the kernel scanned all the devices sitting on that bus, called my_match, found that mydev0 matches the driver name, and fired probe automatically. We didn't call probe. The kernel called it for us. Now look at the Udev monitor. 3 events fired in sequence. The first one, bind/devices/mybus0/mydev0 with subsystem mybus. This is the kernel confirming that the device and driver are now bound together. The second one, add/bus/mybus/drivers/mydev0. The driver is now visible under the bus drivers directory in Sysfs. And the third one, add/module/mydriver. The module itself is now tracked under /sys/module. All 3 of these happened automatically the moment the driver registered. No manual steps, no extra calls, just the device model working exactly as designed. That's the complete Linux device model in action: bus, device, driver, binding, uevents, and Sysfs hierarchy, all from 3 simple kernel modules. Now let's unload everything. And just like loading, the order here matters. We go in reverse. Driver first, then device, then bus. Let's remove the driver. Type sudo rmmod mydriver and hit enter. Look at the kernel log. You can see mydriver remove called from mydev0 printed. Kernel called remove to cleanly detach the driver from the device. That's the lifecycle working in reverse. Now look at the Udev monitor, and this time there's quite a bit happening, so let me walk through it. The first 2 events come from the kernel itself. Unbind/devices/mybus0/mydev0. The kernel is confirming the device and driver have been separated. Then remove/bus/mybus/drivers/mydev0. The driver entry is being removed from the bus drivers directory. Then you see the same 2 events again, but this time from Udev rather than kernel. That's just how Udev works. The kernel fires the event first, then Udev processes it and logs its own confirmation. So every event appears twice, once when the kernel sends it, and once when Udev handles it. And finally, remove/module/mydriver, again from both kernel and Udev, confirming the module itself has been fully unloaded and removed from /sys/module. So in one rmmod command, the kernel automatically unbound the driver, called remove, cleaned up all the Sysfs entries, and notified user space through uevents. All in the correct order, all handled by the device model. Now let's unload the device module. Type sudo rmmod mydevice and hit enter. Look at the kernel log. You can see mydevice exit printed. The device module is unloading, and my _unregister_device is being called, which internally calls device_unregister to remove mydev0 from the bus. Now look at the Udev monitor. This time we have 4 events, 2 from the kernel and 2 from Udev, same pattern as before. Remove/devices/mybus0/mydev0. The device is being removed from the device hierarchy. The mydev0 directory that was sitting under mybus0 in Sysfs is now gone. And remove/module/mydevice. The module itself is fully unloaded, and its entry under /sys/module/ is removed. Again, each event appears once from the kernel and once from Udev, confirming it was handled. Notice something important here. There was no unbind event this time. That's because we already removed the driver in the previous step. By the time we unload the device, there's nothing bound to it anymore. So the kernel just removes the device cleanly with no unbinding needed. And finally, let's unload the bus module. Type sudo rmmod mybus and hit enter. Look at the kernel log. You can see mybus exit printed, followed immediately by mybus release called. That second line is important. The release function on the parent bus device, my_bus_release, is being called as the reference count on that device hits 0. That's the Kobject reference counting we talked about right at the beginning of this video. The object is only freed when nothing is holding a reference to it anymore. Now look at the Udev monitor. Again, 4 events, 2 from the kernel and 2 from Udev. Remove /bus/mybus. The entire bus is being removed from Sysfs. The /sys/bus/mybus directory that we saw created when we loaded the first module is now completely gone. And remove /module/mybus. The module itself is fully unloaded and cleaned up from /sys/module. And that's it. Everything is clean. If you run ls/sys/bus now, my bus is no longer listed. No leftover directories, no dangling entries, no resource leaks. The system is back to exactly the state it was before we loaded anything. That's the complete Linux device model lifecycle, from registration all the way through to clean removal, buses, devices, drivers, Sysfs, uevents, reference counting, and the kernel binding engine, all working together exactly as designed. In the next video, we'll go deeper into the Sysfs interface and look at how to expose driver data to user space through attribute files. If you found this helpful, please give it a like and share it with anyone who's getting into Linux kernel development. And if you haven't subscribed yet, make sure you do. There's a lot more coming in this series. See you in the next one.